We're going to look at topic 18 and see how we can apply Desmos to this. And the first problem we're going to do is page 100, number 5Q. And I've entered this equation in here. And I get this number here as the solution. I'm going to simplify this, and instead of 125, I'm going to write 25 times 5. Instead of 45 here, I'm going to write 9 times 5, and instead of 20, I'm going to write 4 root 5. Now, the reason I've done this is because 25 is 5 squared, perfect square, so I can take the 5 outside the root sign. 9 is 3 squared. I can take the 3 outside the root sign, and 4 is 2 squared. So when I'm doing this, in each one of these numbers here, I look for a perfect square, and 25, 9, and 4 were the perfect squares. So now when I take the 5 outside, I get 5 times 2 is 10. The 5 is still left under the root sign. 3, square root of 3 squared is 3. 3 times 4 is 12. I get that. The 5 is still under the root sign. And here I take out the 2. 6 times 2 is 12, and I get 12 root 5. So now I can factor out root 5, and 10 minus 12 is minus 2, and minus 2 and minus 12 is minus 14, so I get minus 14 root 5. Notice this number doesn't change, and so this becomes a useful way of verifying that we've done the problem correct. Now we'll go to 101.6n, and here we have this term in brackets and this term in brackets. So what I'm going to do is take the root 2 first of all and multiply it by every term in the second bracket. Then I'll take plus root 3 and multiply it by every term in the second bracket. Then I'll take minus root 5 and multiply it by every term in the second bracket. So I should have 9 terms at the end. Root 2 times root 2 gives me 2. Root 2 times root 3 gives me root 6. And root 2 times root 5, the third term here, gives me root 10. Now I'm going to take root 3, multiply it by root 2, I get root 6. Root 3 multiplied by root 3 gives me 3, and root 3 multiplied by, root 3 multiplied by root 5 will give me root 15. And I'll take the last term. This times this gives me root 10. This times this gives me minus root 15. And minus 5 times minus root 5 plus root 5 gives me minus 5. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. Check site. And the number does stay the same. Now I group all terms, and essentially let's see what happens here. The only thing that we're left with is this term, and this term cancels with that term. And we have the 2 and the 3 and the 5 is 0. Anything with root plus root 6 numbers change. So that's the way to slide and go to 1 more complicated problem. First thing I do is enter on here, rewrite this part multiplied by the times, which is whatever we're going to make here with a plus sign. So here it is right here. This is multiply by this. So now the first times the first gives me 175 times 3. And then I'm going to say minus 4 root 2 times 7 root 3 is going to give me minus 28 root 6. So I get this term over here. And if I multiply the outer one, 5 root 2 times 25 root 3, I'm going to get 25 root 6. So these are the inner and outer terms. And the last times the last will give me minus 4 root 2 times plus 5 root 2 will give me 20 times 2. And because this is a minus and that's a plus, it's minus 40. So we're just expanding this by the FOIL method. Do the same thing over here, except it's an a squared minus b squared. So I just take this, square it, which is 49 times 3 minus b squared, which is 5 times 5, which is 25, and root 2 times root 2, which is 2. Now, when I add this, which will be, let's see, 525 minus 40, I get 485. So combining this term with this one, I get 485, and plus 125 root 6 minus 28 root 6 gives me 97 root 6. This is 147. This is 50. So this becomes, this I don't change, the numerator I don't change, this minus this becomes this. Notice the numbers don't change. And so that's very, very important. Tells us that we're doing the problem right. Now I divide 97 into 485, I get 5. I did not divide 97 into this, I get root 6. And of course, because there's a plus here. So this simplifies to that. So that shows us we can do quite a more complicated problem. Now we're going to do something with exponents. We're going to solve this one right here. It's 108, number 80. And so first thing, we enter the problem right here. Instead of 27, I'm going to write 3 cubed. This I'm going to keep the same. 64 is 4 cubed, and b to the minus 3 stays the same. Notice the value doesn't change. You should change the value of the sliders to make sure these don't change. Now I go to the next step, and instead of, I'm going to show, I'm going to take 3 cubed. This I've got 4 cubed. Now I'm going to apply the power rule right over here. So I get 3 cubed to the minus 1/3, a to the minus 3 to the 1/3, 4 cubed to the minus 1/3 right here, and b to the minus 3 to the minus 1/3. So I'm applying this to each one of these individual terms. Okay, so 3 times 1/3 minus 1/3 gives me the minus 1. Same thing over here. Minus 3 times minus 1/3 gives me 3/3, which is plus 1. This one is 3 divided by minus 1/3. You can look at it as multiplication of 3 times minus 1/3 gives me minus 1. And this times that will give me b to the 1. Now I move this down because it's 3 to the minus 1. This is an implied 3 to the 1. And I move this up and it becomes 4a over 3b. These don't change because they have positive exponents. I'm leaving everything with positive exponents, and there's the answer, and that's a simplification. This one's a little more complicated. So we enter, first of all, any number that we want, and then I rewrite this in terms of a instead of the x. And what I have here, what I'm going to do is I'm going to multiply this times this by distributive rule. So I'm going to multiply this times this, and then I'm going to multiply this times this, and I'm going to leave this alone. So this times this gives me that. It's not going to change because I'm multiplying by 1. Root 3 over a times 3 over a. This stays outside the radical sign, and this is inside the radical sign. Now the root of 3 divided by the root of a is the root of 3 over root a. And that's just to see that we can multiply these two together, and we can multiply these two together. So I can change this to that without any problem. This I've left the same. 16 stays the same. Now I'm going to multiply this term by this one, add this one times this one. So root 3a times this one gives me this right here. And then I'm going to do plus, which is this plus here, and I've got to multiply this times this. This is like saying a plus b, and this is c. So you really have a times c, and then plus b times c. If you want, you could move this over to here, and then it would be easier to see. And then you'd multiply this times this, and then this times that. But you're going to get exactly the same thing. So you see the number doesn't change. I multiplied this times that, gives me this term. And this time, second one is this times that, and that gives me this one. And I haven't simplified anything. I just used the distributive rule. Nothing has changed. Now, the root 3 and the root 3 will cancel here because they're the same. And then I'm left with 2a to the 3 halves. And I'm bringing this up, and it's the square root of a, so I'm going to call it minus the square root of a, or a to the minus a half, because this is a to the power 1, and then there's an implied 2 here. So I bring that up. The root 3 and the root 3 cancels. This stays the same, and I bring this a up, and it becomes a to the minus a half. Here, the root 3's cancel, and I have 2 times 3, which gives me the 6. I have the a to the 3 halves, which is this term right here. I bring this term up. It's a to the 1. It becomes a to the minus 1. I bring this term up, which is a to the half, and it becomes a to the minus half. So I move this from the denominator to the numerator, and this from the denominator to the numerator, and I get this. Now, 3 halves minus a half gives me 1, so I get 2a to the 1. I don't need to put the 1 in. 3 halves minus a half is 1 1/2 minus a half is 1. 1 minus 1 is 0, so I have a to the 0, which is 1. So I'm going to just leave a 6 here. In other words, the 3 halves, the minus 1/2, and the minus 1 sum to 0. A to the 0 is 1, so I don't need to put it in. I'm only left with the 6. So you can see that we can simplify that problem quite easily. Is x minus 2 plus root 10 over 3 a solution of this? So I put a equal to this term here, and just calculate 3a squared plus 4a minus 2, and the answer is 0. So since it is 0, put this number in, told this equation that a equals this, and when it calculates this with this value of a, it's 0. So this is a valid solution. Now there's another way of doing that. Maybe you'll like it better. I put the equation of the graph in. I get 2 solutions, minus 17208 or 0.3874. Well, I really don't know what those numbers are, but what I did is I typed in minus 2 plus root 10 over 3, and of course it is the same as this value, so obviously this must be a solution because it's telling me one solution is 387 right here, 4, and then when I type this value in, it's the same thing. So this value here represents this value along the y-axis when x equals 0. And you say, well, what about this other value? What about this? Well, I think the only difference here is that if you put in minus 2 minus root 10, which you get from minus b plus or minus b squared minus 4ac, then you would get the same solution. You would get the minus 172. So that's just minus 2 we change this to minus root 10 over 3, we will get this solution right here. Okay, use the distance formula to show that minus 7, minus 7, minus 1, 1, and 2, 5 are collinear. So what I've done is I've entered distance formulas. And I know this, I probably should have done this a little differently, but I put in distance formulas. And then I've identified x1, y1, x2, y2 as these points here. So x1 is minus 7, y1 is minus 7, x2 is minus 1, y2 is 1. Doesn't matter that I put these in afterwards. It still calculates them here, but it won't calculate this distance until you put these values in. So I put a formula in, and you can see that I got the distances 15, 10, 15, 5. I'll go into that in a little bit. I also, what I did was I put the points in, the 3 points, and plotted them with this notation here. So they appear on the graph right here. So this is like this. Here are the 3 points. Where's minus 7, 7? Here's minus 7, 7. Here's minus 1, 1. That's this point right here. And this point is 2, 5. Now, I also put this in so you could just put in these, and these are generic. So this is specific, but these are generic. So if I vary the values of x1, y1, x2, y2, or whatever I want, automatically this formula would change. So the nice thing about using generic values is that, or values that you can use in any situation, if you change the value of the slider, then these distances will automatically change, rather than just using these values directly into the formula. So this makes it something, if you change the value, if you come to another problem, you can just go back to this template and use it again. So let me give you a little more detailed information. All I'm going to do is copy this information onto another onto the exact same thing, but put in this notation which I put in with red lines. So the distance here is 15, and that's the difference between minus 7. Obviously, it's the distance between this point and that point. So the distance between that point and that point is 15. The distance between this point and that point is 10, and the distance between this and this is 5. These are all my notations with the red arrows, and I'm just doing that to explain what's going on. So if these points were not lying on a straight line, then 10 and 5 would not sum to be 15. That's how you know they're lying on a straight line, is that when you add 10 and 5, they come out to the value between here and here, the distance between here and here. If they were not on a straight line, this distance would not equal 15. So that's just something to show. And over here, I just removed the specific values, left the generic values, and changed one of the values. Below, we have changed only the entry in box 4 from minus 7 to 3. So from box 4, what does it say here? From minus 7 to minus 3. So this value was changed. And you can see now when you look on the graph, the points don't lie on a straight line. This, if you connect these points here, it's not very good. I can't show it very well, but my hand's a little shaky. But you can see that this does not lie on the line that connects this point and that point. So that's just some additional information. Okay, the last problem on page 102. We've got this triangle right here, and we put it in the Pythagorean theorem. We square this, we get this, we square that, we get this, and we square the 8 root 9. We're applying the Pythagoras theorem, and look, he gives us the values of 8 or 5. Now we can't use a negative number as a distance here, so only 8 is a valid answer. Now if I plot this as y equal to, bring this on the other side, square it, because it's squared, of course, and plot this, you can see the solutions come out to be -5 and 8. This graph goes down like this, goes way down, and then comes back up. So this is along the y-axis, along the y-axis, yes, and the x-intercepts are, the y value is 0 here, okay? I don't know what I said there. This is the x-axis, excuse me. This is the x-axis, and y equals 0 along the x-axis. And the two x-intercepts are -5 and 8, and that agrees with the value here. So we can see here, we can get a solution algebraically, and here we get a solution obtained with a graph. But they both give the same answer. So the calculation can be obtained with an equation or a graph. So this completes our discussion on roots and radicals and topic 18.